Hey everyone, my name's Corey. Thank you very much for the introduction, Steve, and Chris for an awesome presentation. My name's Corey, and I'm here to talk to you today about stream processing at Answers. So just take a quick straw poll of the room. How many people have done stream processing before? So we got some hands up, cool. How many people have used Storm before? Okay, so people have heard about Storm. So the goal of this talk is kind of somewhere in between. It's going to give kind of an introduction a little bit about stream processing and why it might be important. Talk a little bit about how Storm, which is kind of the current state of the art, works. And then give an overview of Heron, which is Twitter's next generation stream processing. So before I really get into things, I want to give you a quick overview of what Answers actually is. Answers is a real-time and opinionated mobile analytics product. There are many different mobile analytics products out there in this space. From the beginning, we wanted to differentiate ourselves. The goal for our product was really to be opinionated and give people only the insights that they needed, rather than having them sift through all the data. And we wanted to be able to be real-time, to be the pulse of people's apps. It's no use if your analytics product tells you a week later that you're out of users. You want to know right now and in advance and better. Here's an example of the type of dashboards we present to users. You can see that all metrics on the dashboard fluctuate in real time as we receive new data into the system. Across the top, you see the top 6 metrics that we show. We've chosen 6 metrics that we think are important for all customers to watch. We show these front and center. We show a spark line underneath them to give you context about how you're trending over time. And when there's a big change, we highlight it. You can see kind of an orange circle down here and invite customers to dig in. So this is a really cool dashboard, but how do we actually build it? Answers uses what is known as the Lambda Architecture to power our dashboards. Some of you may have heard of the Lambda Architecture before, but as a brief overview, the Lambda Architecture calls for 2 discrete layers. You have a batch layer and a real-time speed layer. As new data enters the system, it's processed in parallel by both layers. On the one hand, you have a batch layer, which uses Hadoop and MapReduce to compute some view over some set of data. You could build an analytics product using just a batch layer, but the problem is it would be at least an hour or a few hours delayed. These kind of jobs are batch jobs and take a while to compute. In order to remedy that, we in parallel add a real-time layer. This layer computes similar metrics in real time, provides up-to-date results. At query time, the 2 views are merged and joined to provide both an accurate view of the world as well as the most recent one. While both layers are interesting and have their own challenges, as we talked about, Spark R is a great chance for using batch processing. Today I want to focus on the real-time layer, so maybe you get a little bit like the Lambda architecture between the 2 talks. The real-time layer is pretty different from the batch processing. It has a bunch of different concerns that are a little bit different. Unlike the batch layer, the real-time layer has to handle an unbounded stream of new data. Data continues to enter the new system, and there's a hard time requirement for it. We need to be able to process the information in real time to provide low latency results and updates. So let's go ahead and zoom in on the real-time layer and take a look at how it actually works. For us, data starts on devices distributed throughout the world. A user clicks a button or installs an app, and the device sends the information up to a backend we run in AWS. That backend is really simple and has really one task: to put the data into a durable queue. Once the data is safely in a durable queue, we can then begin the process of streaming the data through a series of different processes. This decoupling of receiving the data and actually processing it is actually pretty substantial. It has a number of good advantages. First, let's simplify. We can write code that just handles events reception and writes it to a queue. That's a really simple task, hard to mess up. And then we can write a series of processing tasks that are totally decoupled. This lets us scale them individually. Say if in the future we wanted to add a super advanced processing step that required machine learning, we could go ahead and add that with no impact to our event reception. But it also allows us to handle partial availability nicely. If we imagine for some reason I deployed a bug in our processing pipeline and we can no longer process new events, it's okay. We can still receive them and we'll continue to get new data. We won't lose anything. This is important. By embracing this sort of an asynchronous approach to communication, it allows us to decouple our application into a bunch of different small components that communicate through queues. While this approach has its advantages, building a real-time distributed system in this fashion also has its own challenges. In a system like this, there are many different moving parts. There are a number of different queues, a number of different workers. They all have to be managed, and they have to interconnect. With so many components distributed throughout the system, there are many different failure points. How can you be sure that the data that you received in the front door actually makes it out at the end? It's a real challenge. Further, as we interconnect these systems and they flow through queues, we need to have a way to actually propagate back pressure through a system. If we imagine that one worker somewhere becomes slow, it'll stop reading from a queue at the same rate. That queue might build up in terms of the number of events stuck in it. And if workers writing to that queue don't know about it, that queue will eventually fall over. And that'll result in a loss of data. And that's unacceptable. In 2011, Twitter open sourced a project called Storm, some of you may know. Storm provides a number of abstractions and a clustering system to actually run streaming computations and make it easier, so you don't have to manage all these queues yourself. Storm has a number of abstractions that really help make things simpler. The first abstraction that Storm uses is that of a spout. In Storm, a spout is a source of tuples into the system. It encapsulates the logic of transforming information from a queue or a database, or really anything, into tuples in the system. Storm also has the idea of a bolt. It's a computation on a stream of tuples. This is really the workhorse of the system and where you put the majority of your logic. A bolt processes tuples from spouts and can combine them, filter them, or do operations on them, and potentially also emit tuples. With these two abstractions combined, Storm forms a directed graph of computation. Data starts flowing from spouts and flows through bolts, and eventually ends. That's a little bit abstract, so let's make it a little bit more concrete. Let's take the example of a topology that we want to actually archive data. Let's imagine that we have a bunch of data in a queue somewhere, and we want to write it to S3 efficiently in a way that's scalable. The way we do that is to create a spout and two bolts. The spout would encapsulate the logic of actually reading from the queue, and we create two bolts, one which handled the task of decompressing the events, and another which handled the logic of actually writing them to S3. Once we've defined a topology in Storm, it gives us a huge advantage to be able to scale things linearly. Once you define this shape, you can go ahead and add capacity to a component individually without touching others. As you can imagine, let's say we invented a really good compression algorithm and extraction became expensive. Well, we could go ahead and parallelize extraction, but not affect the amount of time we spend writing to S3 or scale out those workers. That's a huge win. With a topology defined, Storm also helps actually deploying this topology and scheduling it across the cluster. As you remembered, there are many different roles, there are queues and workers, and scheduling and deploying them is a challenge. Storm helps. To deploy a topology in Storm, you submit a configuration in a jar to Nimbus. Nimbus is this kind of cluster management system. Nimbus then communicates with a series of Storm workers through their supervisor and develops an assignment for them. It determines which workers it should run it on and which executors to go ahead and run it in. Storm will then automatically schedule your actual task across the cluster in a way that's reliable. Supervisors will continue to watch processes in case they fail and automatically restart them. And if any worker dies, they'll automatically be rebalanced across the cluster. This is great because it'd be a headache to do by hand. But now that tasks are distributed across the cluster, how do they actually communicate? We've got these tasks that we know need to pass information, and Storm now needs to provide a way to actually communicate between them and pass tuples. In order to provide a robust way to communicate, Storm actually provides a message queue co-resident with the bolt. That means Storm actually runs a 0MQ instance right in front of the bolt. For a spout to actually talk to a bolt, it simply writes data to the 0MQ sitting right next to the bolt. A bolt then pulls information from the queue and begins to process it. But if we backtrack a little while ago, in the beginning I talked about back pressure. We talked about something getting slow and ensuring that people upstream of it knew what was going on. With this sort of an architecture, there's no way for a spout to know immediately if it should back off. This is a one-directional flow. A spout could continue writing data until eventually the 0MQ fell over. That would result in data loss, which is again something we don't want. So, in order to actually implement back pressure in Storm, it must track tuples. For every tuple in the system, Storm actually tracks its acquisition, and sending throughout the whole system. Let's say you have a spout which emits a tuple. It'll go ahead and get passed to the queue on the bolt, and the bolt will eventually pull the tuple out and process it. Once it has successfully processed the tuple, it'll send an acknowledgement back to the spout, and the spout will now know that it can send more data. In this way, a spout can actually regulate how much data flows through the system by keeping this kind of like a max spout pending, it's called. Now, Storm is an amazing system, and we've used it for many years. We've used it both at Crashlytics, which is the precursor to Answers, as well as Twitter. But as with any tool you scale, you find its pain points. Answers has been around for about 2 years, and we've been scaling aggressively since then. We now process more than 1.5 million events every second. That means depending on how slowly or fast I've been talking, we've processed about 1 billion events. Now, that's amazing, but it also comes with its own challenges. And today I want to talk to you about 2 of them. One challenge we've had with Storm in particular is a response to resource utilization. In Storm, as I discussed, there's a way to describe a cluster and run your code across it. To do this, Storm has the idea of a worker, which is a supervisor in some predefined number of slots. These slots represent executor slots, where Storm can schedule work. Now, one challenge here is that you must predefine out how many slots are available for scheduling work across your cluster. While these slots are predefined, workloads are actually diverse in nature. And once a component is scheduled inside of an executor, the rest of the container cannot be used. These are simply JVMs that run code in. As you can see here, schedule a bunch of tasks, and the results in a lot of waste. Further, these tasks are actually competing for resources on the underlying host. Imagine if you had one task which was really I/O heavy or really heavy on CPU usage. It might steal CPU from other tasks and that result in a noisy neighbor. This makes it difficult to debug topologies. It may be running successfully one moment, someone deploys another action, and then you have trouble. It's a challenge. But further, in Storm, the cluster is actually shared between a number of topologies. This means that not only will your own code be running, potentially other teams or potentially other systems are also running. And these again can be scheduled on the same physical host. This not only makes it difficult to actually understand the performance characteristics of your application, but it becomes difficult to debug. To find the log files, you have to go across a number of different machines, and they may be interwoven. With Storm, we're able to work around these in a number of different ways. With response to resource utilization, we actually are able to develop a bunch of different clusters and kind of mess around with the different levels of RAM, CPU, and number of workers scheduled to find some kind of a sweet spot for us. We also ran a couple different clusters. You can imagine we have one cluster which was only for really I/O heavy tasks that were really underloaded, and one which was better for CPU. But there's some overhead here. There's shared components that they actually require. There's also just operational overhead of knowing which cluster to submit to. It's a challenge. Second challenge we had, as we discussed, was back pressure in Storm. While Storm has a way to implement back pressure using sending acknowledgements and tracking ACKing, there's a huge overhead to that. As we scaled up, we had trouble actually maintaining acknowledgements in our system, and so we had to disable them. And that meant with Storm, we had no ability to have back pressure. While it's okay for us to lose some tuples because we have a Lambda architecture, which means that any data we miss during the speed layer, we can then recover in the batch layer, living without back pressure was a real challenge. Twitter has used Heron similarly for many years and has many of the same challenges that we had, and has developed a next generation stream processing tool called Heron to replace it. Twitter's been running Heron in production for about 2 years, and in the past 6 months, Answers and Crashlytics have migrated all of our topologies over to Heron with great success. Heron is API compatible with Storm. This is huge. It's the successor to Storm, and it's 100% API compatible. This enabled us to migrate more than 70 topologies in the past 6 months. Migrations, for anyone else who hasn't done them, is usually a nightmare. This one went pretty well. So, is it a question or?
I guess just very quickly, just to remember, topology is a graph in your install. Right?
Exactly. Sorry. Well, there are a number of different changes in how Heron actually works on the hood. It's API compatible. But these changes are actually pretty substantial. While Storm solves the problem of cluster management using Nimbus and a series of workers, Heron actually outsources this to popular systems that are already deployed in clusters. To do this, Heron uses Mesos and Aurora. Mesos, if for anyone who doesn't know, may know, is a cluster management system that specializes in isolation and efficient resource utilization. And Aurora is a long-time running service scheduler. It kind of takes the role of supervisor and maintains containers, ensures they're running, and the processes within them. Now, Heron, since it's based upon Aurora and Mesos, is able to take advantage of this. This means that inside of your topology, you're able to configure at a very fine-grained detail how much CPU and RAM different tasks actually have access to. Going back to our example, we can imagine we can set the number of containers required for our topology to say 2. And we can go ahead and configure the amount of RAM per container. So we could imagine that the bolt needed less information, like an extraction bolt might be a very fast task, but a bolt that's writing to S3 might want to do some sort of buffering, and so we can give that twice as much memory. In Heron, a topology has a slightly different architecture than Storm. In Heron, there's a topology master, which governs the idea of the actual physical assignment of tasks, and a number of containers. These containers each contain a stream manager and a metrics manager, as well as only your code. As we mentioned, these containers are sized to exactly what fits inside of them. This means that in this case, each one only had exactly 1 gig of RAM allocated to it, or roughly there's a little bit of extra room for other things. And each one is isolated to exactly 2 CPUs, and it's guaranteed to actually get that. Now, this container looks sort of similar to the one we showed before with workers in Storm, but it's actually quite different. There's a stream manager, a metrics manager, and just your instances. Now, the metrics manager manages metrics and a few other things that I haven't talked about, which are very important, but the stream manager is actually new and pretty interesting. The stream manager is involved in message passing, and this is one of the places that Heron really deviates from Storm. In Heron, instead of spouts communicating directly with bolts, they communicate through stream managers. A spout will produce a tuple and send it to a stream manager. That stream manager then handles routing it to other stream managers, where it will then eventually communicate it to the bolt. It effectively kind of proxies this communication. Now, what's substantial here is that stream managers are all interconnected. They need the ability to communicate with everyone else. And this bidirectional communication proves extremely important. This bidirectional communication allows Heron to implement back pressure seamlessly without hacking. If we go through kind of the normal flow, we can imagine that some bolt is running, and then for some reason it has to GC or it can't keep up, or requests are slow for some reason. The stream manager, who's providing it information, can realize that this task has become slow and start sending back pressure signals to other stream managers. All these other stream managers can then clamp down on the spouts that they're attached to. Since the spouts are the source of information, they're the streams of tuples into the system, when you clamp down on a spout, it'll stop sending information. This means that no new information is able to enter the system, and slowly we can let the pressure dissipate. Eventually, when waited long enough, the bolt will recover. Once the bolt is recovered, the stream manager again senses that and sends a stop back pressure signal to all the stream managers. The stream managers then allow new data into the system. In this way, Heron can regulate and actively regulate how fast data moves in the system safely. So to give a quick summary of Heron, for any of you who hear about it later again, Heron's 100% API compatible with Storm. It gives you flexible resource distribution and isolation. It provides simple and predictable back pressure, and much, much more. For any of you who've used Storm before, the visualization tools and management are not so good. With Heron, we've invested a lot in them, and you get beautiful graphs of your topology, great inspectability, and great debuggability. This is kind of an overview of like the management console you get when you run the Heron Viz tool. You can see the logical layout of a topology with 3 different stages here. And then you can also see the mapping of the actual tasks to containers. You can inspect them individually and see how each container is performing, as well as at a high level, get an overview of what's going on inside your topology and cluster. Thank you all for coming and listening, and thanks for inviting me. I don't know what's next, but I'm happy to answer any questions now or later or during the Silver Feather talk time. I don't know what that, remember the name of that?
So Heron is one of the solutions for stream processing, right? There's a bunch of others, like, I guess Flink and Spark Streaming. How do they compare to all you have to know?
That's a really good question. So they compared a bunch of different ways, and each kind of has its different specialty. Part of the reason for Twitter working on Heron was we've invested so much in Storm. We also thought that the API it actually provides is good. So the underlying API was good, but the implementation there were some rooms for optimization and improvements. So Twitter opted to improve that area. The other piece is it really specializes in real-timeness. Some of the other streaming engines use kind of batch processing or micro-batching. There's just kind of different strokes. I am.
Are you using a programming language with this that you're building?
Yeah, so it's the Storm and Heron are both like JVM based. So there's interfaces in Java, but also in Scala as well as Clojure. And Heron, similar to Storm, has like kind of an abstract interface so that any language could actually implement it and connect with it.
Can you repeat the question?
Yes, sorry.
Is it 0MQ based?
It is not.
Okay.
It does not use ZRMQ at all. Which actually, if you use Storm, it's actually one of the challenges with it. There's these large queues that are not possible to inspect easily. So Heron completely does away with those. And as part of that, we get huge performance gains, predictability. I don't have any slides about the performance in particular. There's a blog post by Twitter, actually, I think about 6 months ago, by Karthik, that talks about the performance gains, which were substantial.
Do you run Heron on EC2?
We do, yeah. So all of our stuff is hosted on AWS. So we run Mesos on EC2, and we run all of our work against that.
How do the stream managers communicate with each other? Do they have any specific protocol?
It's all done over Thrift. So they all use Thrift structures internally and communicate over Thrift.
Is Heron open source?
Heron is not currently open source. There are definitely plans to kind of move in that direction, but no kind of firm kind of deadline. The team is definitely very interested in it.
What are your supervisor queues? The queues that you have in supervisors?
In the stream manager, so the stream managers in Heron actually have very small queues. They're actually like about 60 elements deep, and they're kind of just simple blocking queues that are in memory. Part of the advantage is actually keeping it inside of the same process. One of the challenges that is faced kind of in Storm is there's actually a lot of stuff going on. There's Clojure running, there's ZRMQ running, there's a bunch of different things that you're interacting with. That has implications both operationally, but also in terms of performance. So under the covers, Heron is actually mostly written in C, C++, and kind of keeps that all stuff in-house and is able to optimize pretty aggressively.
I have one more question. So the batch pressure signals go out to each of the individual bolts, right? What if a message is lost during the transmission? What do you do?
So Heron also has like similar message processing guarantees, so it can actually implement hacking as well. So back pressure mechanism can let it actually translate like velocity, but not for tracking individual messages. That's a really good point. I forgot to repeat. Sorry, go ahead.
Wouldn't the dropping use stream manager have some problems of dropping the messages if the backlog increases in capacity?
It's a good question. So when there's queues on either side of a stream manager, there's an in queue for it receiving data, as well as an out queue for it providing it to bolts. So what happens if a stream manager can actually block when sending data to another stream manager, it can go ahead and propagate that back to the bolt that's receiving it and still send that stop back pressure signal. If it slows down either on the sending, like on the sending side of data, new data coming into it, or else on the giving data to the bolt next to it, it can still send the same back pressure signal. Does that make sense?
What do you guys use for deploying and managing topologies when you want to introduce something into your environment?
So the nice thing about this is we use Mesos. So the way you submit a Heron topology is you run a command line, and effectively it creates a bunch of tasks inside of Mesos that then get scheduled. So we create jars and simply deploy them. We use our own kind of like chat ops system that's based on Chef and hosted Chef internally.
Can this be run in conjunction with other things like Storm and other?
It can. It's kind of a replacement for Storm. So you wouldn't typically run them both. But the nice thing is that you simply have to change a dependency on Storm inside of your topology, and you'll be pretty much able to run it on Heron. There's a few changes around serialization that you might come into, but that's it.
So you might have missed a point. Does this also run on microbatches as strong?
Does it run on what?
Microbatches.
It does do microbatching internally and is able to manage that. But in Storm, the microbatching is actually done by the 0MQ, because implicit inside of 0MQ is microbatching. Heron can actually do that explicitly in a different sense. So it doesn't kind of outsource that. I actually don't know what the setting is or if it's configurable. That was the question.
Yeah, so if I remember it right, the Storm's least microbatch was controlled at like 1 second intervals or something.
Okay.
Does it have a similar restriction?
No, it does not have a similar restriction that I know of. We can talk more. We should figure this out.
So Lisa, the question is this how Twitter processes all of the tweets that it comes from all over the world?
Yeah, so Twitter uses Heron to process all of our real-time systems. So every single tweet will flow through a number of different Heron topologies.
So does that include like imagery and
That's a good question. I don't know exactly what those teams use for each portion of it. I know some of it definitely does. But there's a variety of different things deployed at Twitter. But for everything that we used to use Storm for, we now use Heron.
Oh, one question. So when you specify the topology, I noticed that you provided some sort of system parameters, like how much, this much memory, this much CPU. What if you don't provide that? Do you have sensible defaults for that?
They're pretty sensible defaults. I think they may be tuned to the current use cases that we've used it for, so they might not be the same for everyone in the world. But right now, the defaults are pretty sane. You get a CPU per task and a gig of memory per JVM. There's obviously room to change those defaults and make them more configurable. Awesome. Thank you all for listening and for your questions. I'll be hanging around and would love to talk more. Oh.
Do you have the cost is like almost like 70-30 kind of stuff, or how does it work?
Sorry, I don't think I
The
understand.
cost of using your service, kind of.
There's no cost to use, like Heron is a replacement for Storm. There were significant cost reductions in actually moving to Heron because it's a lot more efficient and because the resource management actually makes it a lot easier to schedule things. I can't share any numbers about the exact cost. There's a blog post where Twitter talks about its change in costs, and they were fairly substantial.
Initially, you mentioned like one of the inspirations for Storm and Heron was to be able to merge batch process and real-time data. So how do you do that? I mean, do you have like custom programs or?
Yeah, so I should probably, oh, sorry, the question was, in the beginning I was talking about the Lambda architecture, and kind of a combination between like real-time processing and batch processing. I believe the question was kind of how do you merge them in the end, at the end, and does Heron help, and do we have anything else to do it? The first piece is that Heron actually doesn't help with doing batch processing at all. It focuses purely on the real-time side of things. But Twitter has a number of open source, I believe open source framework, it does, yeah, called Hummingbird, which provides a combined API for creating something that's both streaming and batch processing. And Twitter uses that a lot internally. I haven't actually used it personally, so I can't speak to it. But there are a number of different tools to help you manage that complexity, and it's a really good area of research, which goes back to kind of the combination of other stream processing languages and the differences between them.